Thank you very much. I'm sorry I couldn't be there in person. I'm very excited for the 10-year anniversary of the flyby. Pluto was simply amazing, and I hope you all enjoy the week at APL. Um, so I'm going to be the first of two talks talking about the energy budget of Pluto. And my apologies, there's a Mac to Windows font issue, but you know that that word is Pluto. I'm sure there'll be errors throughout, but um, next, please. So why do we care about energy budgets? Here I show a lovely David Hardy illustration done before the encounter of what Pluto might look like. And simply put, Pluto's at the edge of the solar system. As I'll go into details later, it doesn't experience any tidal heating at present. So there's not really a lot of energy there to do amazing geology, and yet we see amazing geology. And so how does that happen? And one way to look at this is by cataloging the inputs of energy. Next slide, please. So Will and I kind of split up this energy budget tag team into two parts. I'm going to talk about sort of the deeper time aspects of Pluto's energy budget, including mostly things on the interior of Pluto, whereas Will talk more about present day processes and things like solar insolation, charged particles, and the like. Before I get into it, I want to preface this. I am not an expert on everything I'm going to be talking about. There has been so much work that's gone into understanding Pluto's energy budget with time by a vast number of authors. So you'll see lots of citations in the footnotes of these slides. Um, and I think so just that's both giving myself an out, but also I want to acknowledge the amount of work that's gone into this. Next slide. So I'm just going to kind of step through some different energy sources. The first, at least chronologically, to think about is the energy from accretion. And so on the left, you can see an example of a streaming instability type model for producing Kuiper belt objects, planetesimals, things that might look like Pluto. And there's actually been a huge renaissance in our understanding of the formation of planetesimals in the last 10 years. Um, but at a very low level, you can estimate the amount of energy that's being released, or at least the minimum amount of energy that's being released by just tracking the gravitational potential energy that's released when you put together an object the size of Pluto. And so throughout this talk, I'm going to show a bunch of numbers. Um, the amount of energy released via accretion is something of the order of 5.7, and I had to look it up, octillion joules, 10 to the 27 joules. Um, I'll keep the exponents the same throughout all the slides. So 5.7 in these gigantic joules units. Next slide. So once you've built a planet, or as you're building a planet, there's another way to release gravitational potential or energy, and that's differentiating the planet. So assuming you started with a relatively well-mixed body with rock and ice, which we know just from the bulk density of Pluto that it's some mixture of rock and ice. If you differentiate that and you put all the rock in the middle and all the ice on top, that releases some gravitational potential energy. And on this sort of giant joules unit, it's about 0.8 joules. Next slide. The really exciting thing that happens after you've formed Pluto is the formation of Charon. So Pluto has this enormous moon, Charon or Charon. Here I'm showing an example of one model. This is by Adine Denton and colleagues, the recent sort of kiss and capture hypothesis for the formation of Charon, where you have a large object sort of grazing and then spinning off of Charon. Or off of Pluto. There's a variety of models for the formation of Charon. Almost all are giant impact models these days. And that impact obviously comes with energy. You can estimate that as well by doing effectively, it's another gravitational potential energy calculation. Um, and it's something of the order of 1.5 times 10 to the 27 joules. So it's a very notable amount of energy that's deposited. And at this point, I have to pause for a moment because I'm just reporting these energies as a single number. Of course, the amount of energy deposited during impact, or it's not even really the amount, but how usable that energy is, what it actually does to the planet, uh, is incredibly complicated. It's not always just going into melting ice. It can go into breaking things, fracturing. Um, so I'm just presenting the sort of highest level ranking of the amount of energy going into this world. Next slide. Keeping on the impacts theme, you could, if you listen to the last set of talks, Sputnik is one of the keys to the current geology and the past geology of Pluto. It's the largest preserved impact basin on Pluto that everyone agrees is an impact basin. And here in another model by Adine Denton, you can see a simulation of what this impact may have looked like, um, as this impactor roughly 300 to 600 kilometers in diameter, depending on which paper you're referencing, smacks into Pluto at about 1 to 2 kilometers per second. So this unsurprisingly reshaped the world and gave us the heart that we know to love today. Um, the amount of energy released is obviously a lot less than, say, the Sharon forming impact, and most of the other processes I've talked about thus far. So it's about 0.1 uh, in these energy units. Um, and since this is the largest preserved impact, you can pretty quickly extrapolate to the role of smaller impacts. Although they're more numerous, um, the drop off of energy with, say, size is pretty steep. So I didn't do a calculation for the total integrated number of impacts over time, but as the largest preserved impact, you can see that this is a notable but not huge contributor to Pluto's energy budget. Next slide. Um, I said at the start that I haven't done most of the work in this talk. This is the one example. So true polar wander, meaning the reorientation of Pluto due to redistribution of mass, is something that I have worked extensively on. And buried in the supplement of my 2016 paper, I actually did a calculation looking at the amount of energy that would be released via true polar wander. And so my contribution is that it's nothing, at least on the scale of the energies that we're talking about here. So even though this process is really important for understanding the geology of Pluto, it doesn't have a major contribution to the energy budget of Pluto. And basically, the reason polar wander happens is you have redistribution of mass that changes the moments of inertia of Pluto, and the energy is only proportional to the moments of inertia, and the changes in the moments are really small. So it really doesn't have that much of an effect on the global energy budget. Next slide. Tides and despinning are a really important one. So here's a lovely animation just showing the a Pluto-centered approach animation. So as after Charon formed, it would have been in a closer orbit to Pluto. The two worlds may have been spinning a lot faster, and eventually tides worked to move Charon out to slow down the spins of both Charon and Pluto and put them in the present doubly synchronous configuration we see today. And so you can work out the amount of energy. In this case, it's about 1 in our units. Um, Next slide. Next slide, please. Okay. Um, as a specific example of some recent work that's been done, I'm showing here a bunch of plots by Amir Bagheri, who's currently at Caltech. This is a lovely little paper looking at the orbital and tidal evolution of the Pluto-Charon system over time after it forms. So in these plots, Pluto is blue and Charon is red, and time, like the formation, is on the left, and time increases to the right. So just looking at the top left plot for now, you can see that the two worlds would have started at a higher spin rate, and over time, on average, they slow down due to tides. You can see here there's a couple step functions in Charon's spin orbit configuration. Actually, they predict it goes into different spin orbit resonances, like the 3 to 2, before it eventually becomes synchronous. But eventually, they all slow down. You can look at all these other plots like eccentricity and orbital distance, but the important one is the bottom right, where Amir calculated out the total energy dissipation in both worlds as a function of time. So those are the solid lines. and compare them with the dashed lines to the radiogenic heating. So early on, when all this tidal action is happening, this is a pretty notable effect. Um, it would have been comparable to the amount of radiogenic heating happening within Charon, or sorry, within Pluto. But tides worked really fast in the Pluto-Charon system, and you can see by only 1,000 or 10,000 years after the formation, the amount of tidal dissipation happening is just dropping off. So this would have been important very, very early on, but it quickly becomes irrelevant. Next slide. The biggest powerhouse for energy is just radioactive decay within Pluto. Um, there's a variety of relevant elements. This is pulled from a synthesis by Robichun and Nimmo et al. Um, uh, Part of the challenge is figuring out how long it took to build Pluto, and thus how important the short-lived radioactive elements like aluminum 26 are. Um, Most papers assume that Pluto took a while to build, although there's work challenging that. So some things like potassium and thorium are more important, but this is really the what keeps Pluto alive for a long time. Next slide. A trendy topic in ocean world literature is the role of serpentinization. So serpentinization is a water-rock interaction that happens on Earth. It powers things like, for example, the hydrothermal vents that you see on the screen. And it's basically what happens when you take uh, volcanic rock, expose it to water, and let it evolve. It releases a lot of energy, but it releases less energy than the radiogenic heating. So some ballpark numbers here put it at about 2% of that radiogenic value. So it's not completely negligible, but it's pretty small. The one advantage here is that serpentinization can also last for a long time, depending on the nature of the water rock interaction. Next slide. Okay, so I've just listed off a bunch of things that are providing heat into the system. What can that heat do? Next slide. The thing that everyone cares about is, can it melt Pluto? Can it help produce an ocean? And the answer is yes. If you look at the amount of energy it would take to melt, say, a 200-kilometer thick layer of ice and turn it into water, it's about 1 in our units. And I've already listed a number of processes that can produce that amount of energy. So it's very plausible to produce a water-rich layer on Pluto. Next. As an example, there's been a lot of work into the thermal evolution of Pluto. I'm just showing one example model. This is by Shun Kamada et al. There's actually two models here. These are both looking at the evolution of the ice shell temperature with time. On the left is Pluto without a methane clathrate layer at the bottom of the ice shell. The one on the right is. And even without these sort of things that can keep an ocean alive for longer, you can see that you can have a very long-lived ocean, potentially even to today. Next slide. That said, I want to bring up an important asterisk with the Pluto's ocean. And this is like the one hill I'll always bring up. I think it's really important for us to remember that the existence of Pluto's ocean is a hypothesis. I think it's a very good hypothesis. It's based on a lot of evidence, um, which you can see a good review of in Nimmo and McKinnon et al. Things like the absence of a fossil bulge, um, the absence of compressional tectonics, uh, cryovolcanic features, and then probably I think the strongest is the true polar wander hypothesis. But each of these have little kinks and asterisks on them as well. So while I do think that Pluto is an excellent candidate for an ocean world, I just want to remind everyone that there's always more work to do here. And for example, next slide, just to highlight some additional recent work. So this is by Ballantine et al. This is an impact simulation where they looked at the formation of Sputnik uh, in an oceanless Pluto, and they found that they can create a Sputnik-like structure and Sputnik-like mass anomaly without the presence of an ocean. So I'm not going to say whether I think this is right or not, but it's important, as someone who thinks about ocean worlds a lot, that we keep our assumptions straight. Next. There are a variety of other geologic processes that can take up heat, and I'm not going to go through them all just for the lack of time. Things like cryovolcanism, things like convection. I'm showing convection cells in Sputnik, but you could also imagine dynamics in the underlying ice, especially ice close to the ocean that's warmer. So there's all sorts of things that can eat up this energy with time. Next slide. And so this is my last slide. A summary. Oh, despite being at the edge of the solar system, Pluto has sufficient energy to do a lot of the interesting things that we care about. And in the process of making this talk, I was actually really amazed by the amount of work that's happened since the Pluto flyby. There's been a huge wave of new theoretical models, whether that's impact modeling of the Pluto, or so the Sharon forming event, Sputnik, things looking at the accretion, to the thermal evolution, and it really goes to show how transformative the New Horizons flyby was. And I suspect that the ramifications of these studies will be felt across the solar system and beyond. And so with that, I will stop. Thank you.